welcome. For today's webinar, we're going to look at a model of a suction pile under lateral loading in 3D. As we can see from the diagram, there'll be a suction pile that's already in the bottom of the sea, connected by a chain. In this case, we're supposedly modeling a buoy pulling, creating a force, a pull force on the side of the suction pile. And so the pile itself is already embedded in the seabed, which in this case we're going to model as clay. And we're going to vary a series of point loads, nodal force loads, on the side of the suction pile to model what would be the chain itself pulling at different angles. And what we're actually going to do is compare this directly with a Plaxis tutorial. Here's a better or more clear understanding of what it is we're looking at today. So as we see, we're going to be modeling a suction pile with a point load itself, and we'll be looking at results like displacement or force loads. Other things that we'll be looking at today will be the use of interface elements, the use of undrained conditions for the clay, as well as the use of structural elements like shell for these hollow suction piles. And lastly, we'll be comparing results directly with this well-known Plaxis 3D tutorial. So off the bat, this is a chart of the material definition. It's only one material for the ground itself, which will be, as I mentioned, clay. We'll be using more column. And something that we'll be using, some of the features that we have optional we'll be using would be, we'll have a starting point of an elastic modulus, but we'll also be increasing it with depth. And it'll be, the reference point will be the surface, which would be at the level of 0, the global level of 0 meters. 0 meters. And then, as I mentioned, we'll also be using the undrained condition. In this case, we call it B. It's basically the second option from the list, which will become more clear once I open the model or the program. And similarly for the elastic modulus, we'll also be looking at a starting point for cohesion, but also increasing this cohesion from the surface going down. And in terms of the structural component, there'll be steel. We'll be using a constitutive model elastic, and then the properties itself will just be a 2D shell, and we're going to say that the pile wall is around 5 centimeters thick. And then here are the parameters for the interface itself. We're going to actually be using two interfaces. We're going to apply an interface on the outside and then apply an interface with different properties on the inside. And this is just to showcase how to do this in the program and also to directly try to follow the steps that we are comparing with the tutorial that we mentioned from the other program. So from here on out until when we get to the results, I'm going to switch to the program itself. And then in the end, I'll come back to the PPT to look at some of these comparisons for the tutorials and a conclusions slide. So we'll be working on 3D. This is the GTSNX program. At this point, I've already established that we're working in 3D. You can see that the global axis is C vertical. If you go to the analysis tab and go to the settings option, you can verify this or you can modify this if you wanted to. So let me just slide this over here. So first thing we're going to do is define the materials. Go to mesh, material, create, isotropic, and we're going to select from the list more column, and we'll call this clay. And I'm just going to fill in the values as we saw on the table. So this is where you tell the program that the modulus for elasticity is going to be increasing with depth, and you give it a reference height. And you also put in other values like the weight, Poisson ratio, K naught factor. In the porous tab, this is where we will be establishing or fixing the undrained condition. As I mentioned, it'll be, we call it option B, which is just literally the second option of the undrained. So it's effective stiffness and undrained strength. And then lastly, for the nonlinear part, this is where we'll give it the cohesion of 5, and it's increasing with 4, and there's no friction. So we'll apply that, and it's just letting us know that we're using this undrained condition. And then the next will be just the steel itself. Steel material. I'll activate this tab to, we're not going to worry about the, what would be the porosity of condition for the steel. So I'll just add 7 zeros in front of this 21. And then give it the weight. So we have our two materials defined, and then the other thing we need to do is tell the program how we're going to be using these materials, which is what the property is for. So we're going to have one in 3D, which is of course the clay, and one in 2D, which will be the pile walls. In this case, we're going to use that shell element, and as I mentioned, we'll give it a thickness of 5 centimeters. Sorry, 0.5. We see the material selected is steel, and we'll just call this the pile. So right off the bat, that's one of the differences from where we depart from the Plaxis tutorial, if you're familiar with it or not, but they actually don't model the pile as a structural element. What they end up doing is using an object, a geometry, a rigid object as they call it, and so it has no structural properties. It can only manage displacements. They apply a load, and it's just like a rigid object, and so it'll move around, but it won't reflect structural results as we will be able to, like forces or moments acting on the pile itself. So right off the bat, there's one of the differences from us and the Plaxis tutorial. So now we can go on to the geometry. So there's different ways to do this. You can draw 2D and then extrude to make 3D, or you can also directly just create 3D objects. In this case, I'm going to create half the ground as a solid object, and then I'll extrude the pile itself. So you can see here I can drag this around and drop it anywhere I want, and there's coordinates telling me. Or I can directly just input these coordinates. So in this case, I'm giving it dimensions and location. And I can actually preview it and make sure that it's in the right place. So we see here it's nicely centered. It goes, it's 60 wide, but it goes 30 and 30 each way. And it's also 30 deep, the height itself. So we have the first half of what would be our soil layer. Now we're going to draw the location of the pile. For things that are 3D solid geometries, you can drop them anywhere you want. But when you're drawing 2D, we have what this is called, this work plane. You can kind of see that it's here on the ZX plane. So if I want to draw something, it's assisting us since we're working in a 3D environment. It would be very hard without something like a plane to draw something two-dimensional and be able to distinguish the depth of where we want it to be. So this plane helps us for that. So what I gotta do first is I gotta just move it, shift it so that the pilot's sitting, when I draw it, on top of this geometry. So I can go here to the work plane in the works tree and just double click on XY plane. And we see now that this has automatically shifted. And now if I draw something, it'll be in the right location. So I'm gonna draw a circle, a 2D circle, and I'm gonna tell it that I want to make it a face. And as far as location, I'm actually just going to put it at the origin, and then all I got to do is give it a radius. And again, I can draw the radius. Obviously, it would be a little difficult because dimensions of this grid don't quite work for the dimensions of the project we're working. So I'm just going to tell it it's a 5-meter diameter pile, so the radius will be 2.5 meters. And so we see that there. So I no longer need the work grid. I can deactivate it. And what I'm going to do now is I'm just going to extrude the pile itself to make us a cylinder. So I select the object, in this case it's a face. I'm going to select the direction, vertical, and I'm going to tell it that I want it to go 10 meters. And if I preview it, it's negative, so it's going down. So now we have what would be some starting geometry. What I'm going to do now is I'm going to use this command Boolean operation. As it stands now, the program just knows that there's two objects, but he doesn't know how they're going to interact together. So I'm going to embed into the target, the soil, the tool, which is the cylinder. And now it's a more realistic interaction. If I deactivate the surfaces and deactivate one of the solids, we see that the program now recognizes that they're not going to overlap. One is indeed inside the other. So now what I'm going to do is use a command we have called mirror, just to basically reflect this and make a full 3D. So that's another point of departure from the Plaxis tutorial. They do a 3D analysis, but they only model half of the project. So technically it's 3D, but they're not really modeling fully 3D in the sense that their object is cut in half. So here I'm selecting both. I'm going to create a mirror about the CX plane. So I can select it either from here, or I could also select it directly here from the work tree. And I'm going to tell it to just make a copy of this. So we see there now I have a fully 3D geometry. And so we could technically proceed on to meshing, but what I would like to show you is another tool we have called check duplicates that just verifies the contacts between geometries. In this case, we see the faces of the cylinder and between the two sides light up in orange. So that's essentially telling us that the program recognizes that there's a contact. Should we need to fix that, we have this other command called autoconnect, but in this case we're fine. So we could proceed on to meshing. As of now, everything we're going to mesh is going to be with the clay material because they're all 3D objects. Later on, we're actually going to also mesh the 2D pile faces, but as you may know, suction piles are actually hollow inside and they don't have a bottom face, only a top face. So we'll show later how this is achieved when we're trying to model those kind of geometries. For now, let's focus on the soil only, since like inside the pile itself still only has clay, so we will be meshing this cylinder, but we'll be meshing it as clay, and we'll just call it inner soil. I want to give it a size of 1. That means that every 1 meter there will be a location of a node. And what I also want to do in this case is activate the higher order elements. This is to match what's proposed in the Plexus tutorial, but also these kind of elements are usually used when there's going to be a high expectation of this expectation of high displacements in very soft soil. So it can be used for what would be like a settlement analysis on a very soft soil. You can use these higher order elements, but for the most part, also they're associated with slope stability analysis for a higher accuracy. So here we'll just use them. So this will be meshing the inner soil, and I give it a size of 1. And then I'll mesh the outer soil, and I'll give it a size of 3.75 meters. So a larger size. Now the program will automatically, you can see there the distribution of the different size of elements. The program will automatically find a way to connect, to compensate, or to have this gradual change in size. You can kind of see it very clearly if you see the starting size of the elements and how they become closer as they get to the pile. Of course, they have to, since they want the nodes to line up and match and be connected. Well, that's another difference with the Plexus software. They had to use a helper object in between, an additional geometry with a specific mesh size, just so they can get these connections between the inner and the outer layers, whereas we don't have to worry about that. The program is very good about connecting automatically these gradual changes, these different sizes of elements between sets. if we need it, or if we chose to have even more control, we actually have our own commands for controlling the size of the mesh in more advanced ways, where you can tell it even like linear gradings. You can select edges and have a starting size on one end and another size on another within the same geometry. In this case, it's very easy, very straightforward, at least in Midas, because we just have different geometries of specific sizes. So there's no need to control additional different sizes or use additional size control. So now we've meshed the soil only, and what we're gonna do next is create a reference point for where we're gonna apply the load. I'm gonna deactivate the soil layers, the outer soil layers, and I'm gonna go back to geometry and do a 3D point. In this case, since it's 3D, I don't have to worry about the work plane, and I especially don't have to worry about the work plane because I'm gonna draw it directly on my geometry of the pile. So I want it to be exactly on the right side, which we know the diameter is 2.5. We can actually see the grids here. It's telling me on the x-axis 2.5 is the outer edge. So I want it to go then down to the 7-meter point. So this is exactly where I want it, 2.5 to the right, 7 meters down. And if I turn it, it should be exactly in between these two sets. So that's just a reference point to where I'm going to apply my load, but it's much easier to use these coordinate systems with the drawings than when you're trying to guess that point applying the load itself. So next what we're going to do is we're going to create the shell element of the pile itself, and we're going to use a command called extract. So we'll go here to element extract. This command allows us to, as it says, extract mesh sets from existing mesh sets and apply whatever property we want. What's different is that instead of trying to select the elements, we can actually just select the faces of our geometry. And so I'll select from here the type face, since it's a geometry face. And I'm going to select the 4 outer walls and then the top faces. See, we're leaving unselected the bottom, and because it's a shell element, it'll be hollow. It'll leave it hollow inside. So this will just be the pile. And we're already assigning the structural property of pile, but we'll notice that the nodes actually coincide to the location of the already meshed ground, so they're connected. But we see here, this is exactly what we wanted, a hollow pile itself, but the top, it's a suction pile, so the top is also there. So now we have our mesh created, and what we can move on now is to applying the interfaces. So I'll go here to interface. We're gonna use the plane option, and we're gonna select from shell, so this is a shell element. So a few things. First, you select the shell elements. In this case, I'm selecting them all. We see that we can choose to apply the interface either on both faces all at once, or we can choose between additionally normal or negative normal. Normal in this case being on the outer side of the face, since it's normal, it's positive, and negative normal being in the inside. So let's start off first applying the inside interface. I'm gonna activate this option to merge the bottom nodes for stability purposes of the pile. I'm also creating rigid links between as an additional set, and those rigid links will only be used for the construction stage process, and then will be deactivated once the interface kicks in later stages. I'll clarify that a little more once we're going through the definition of the stages themselves. And the last thing we're going to do is we're going to apply the interface using this wizard, as we call it, where you only have to worry about these two main factors, and the program will then calculate the rigidness in the tangent and normal direction. There's a very short explanation in the PDF of how these equations use these two values that are in the TV being the virtual thickness. There's a certain range that's recommended depending on the difference of stiffnesses. And then for R, there's also a range of values recommended depending on the difference of materials between the structure and the soil itself. So typically interfaces are only used for more realistic behavior when there's a very soft ground. So this is why we only see recommendations for clay and sand. And so we're actually gonna, just for the training purpose, not for any practical purpose, we're gonna apply different interfaces values to the inner and the outer, just to show that you can have a lot of control, and even if you wanted to have different values of interfaces, and also to match what we're again following the steps of this Plaxis tutorial that we're comparing to, which is what they do in theirs. So for the inner interface, I'm going to give this a value of 0.1 for TV and a value of 1 for R, and allow water to flow, although it's not a seepage analysis, so that actually won't affect much. And then we'll call this the inner interface, and I'll apply it. And we notice that the symbols are now represented of the interface, and there's actually some on the top face as well. That has to do with the soil being in contact from the inside, touching that top face. So this interface is fine. I can deactivate it, and now we're going to apply an interface to the outer face. Sorry. I'm going to select the elements again. Select now normal direction. I'm going to merge the same bottom nodes for stability. Create rigid links. And then this time for the wizard, just again matching what's happening in the Plaxis tutorial, we're just going to give it a value of 0.7 for the R. So different stiffnesses on each side, and this will be the outer interface. And now when we apply the outer interface, we notice that there's no interface applied to the top elements, the top face of this pile. And that makes sense, since the interface is actually supposed to model what is the interaction, basically the friction between the structure and the ground. And so for the outer interface, the pile itself is buried, but not completely buried. There's no soil above the pile. So it makes sense that there's no interface being generated if we're applying it on the outer side, only on the inside. And if we inspect the materials, we have the two interfaces. They're going to have different values of stiffness for each, since we use different R's. So this being the Kn, the stiffness in the normal direction, and this in the tangent direction, Kt. And so we see one is higher than the other. The first one we use the value of R1, it's higher than when we use the value of R0.7. So we actually have a specific tutorial that goes really into depth for interfaces only. So if you're curious about that, you can request that to us and we will gladly share with you. So now we've created the interfaces, we have everything meshed, and we can get ready now to proceed to what would be applying like boundary conditions and such. So let's proceed to that. We'll go here to apply constraints. The program will do this automatically. We can just, actually, we don't have to select anything. We just tell it to auto apply this. Same with self weight. We just have to make sure that it's in the correct direction. And we'll give it the load set gravity. And now what we're going to do is we're going to get very specific with the point load. As we had mentioned, we're going to apply a force specifically to model what would be the interaction with the chain, the pull force from the chain itself. And what we're going to do is we're going to create 4 sets of loads, of force loads, and we're going to vary the magnitude in the x and z direction to create different angles of pull. So we're going to create one first at 30 degrees. And I'm going to select the specific point, which is actually applying it to the node. So as I mentioned, that's just a geometry reference. And when I apply it, we see here that we have an arrow representing the magnitude in each direction. So of course it makes a 30-degree angle. So we're just going to repeat this for 40, 50, and 60 degrees. The overall magnitude itself will be the same, but by varying the two, we'll be creating these different angles. So for 40 degrees, we'll apply these values. Again, this is from you'll see these values in a table in our tutorial, but this is also from a table in the tutorial we're comparing to against Plaxis. So we just make sure we keep applying it to the same point. And we see there now we have a different arrow, and it's slightly higher as we would expect, 40, and then now we're going to do it for 50 degrees. I have this automatic saver that just come up and told me to save this as I'm progressing, so let's just give it a webinar. Okay. And so this would be, where was I, 50 degrees. Select the object. So we see there the third arrow, and we're just going to do that one more time for 60 degrees. So you see these are the same numbers we applied to the 30-degree load, we're just flipping them. And again, it's only to keep the magnitude the same, but simulate as if we were getting, the different angles. So there we have the four loads, force loads, creating this pull at these four different angles. So now what we're going to do is we're going to model construction stage analysis, and we're going to create a case for each load set. So first off, let's just call this one 30 degrees. We select from the list the stress construction stage analysis, but we see we have many options for the type of construction stage analysis you can do. So we just click add and then define. We're actually not going to model the full suction pile installation process, since that would actually require more like a fully coupled analysis, since there's water being pumped out that's creating a suction force that pulls the pile in. So we're just going to model a stage where the pile itself is installed. What we're really going to focus on is the force pulling on the pile itself. So we'll call this the initial stage. What I want to do now is activate all my mesh sets. And what we see here is we have three tabs. We have the tab for everything we've created, the tab for data to be activated, to be considered in this stage, and then later we'll be showing how this data is deactivated as well when we're simulating excavations or we want sets to no longer be used. So in this case, it's very simple. There's not a lot of sets, but it can get a little tricky to make sure you're activating everything you need just by names. So it's a good practice to have very clear names for your mesh sets. Another trick we also have here is to tell the program to only show you what's been activated up to this point. So now it's very clear, nothing is here, but as I start to drag and drop, things start to appear in the window. So it becomes easier to see if we're missing anything. So of course we want to activate this is the initial stage, so only the soil, but we also need to activate the rigid link set. If you recall, when we created the interfaces, we created the set as well. This is where it's useful. If you're going to be using interfaces, what you're actually doing is you're disconnecting the nodes between the layers to simulate, add this interface that's more like a plane, an additional element that simulates the friction between them. So since these nodes are disconnected, but we're not going to activate the interfaces into the next stage when we activate the pile, we need this rigid link set for stability purposes in the initial stage. So this is why we have it now. We're going to activate the outer boundary condition and then the gravity load. What we also want to define is the water level. We're simulating like we're 50 feet beneath the sea surface, and we want to clear displacements. So now we have the visualization there of the water level as well. So this is stage 1. We go to new stage. This will be the pile being installed. So I'm going to drag and drop the pile, drag and drop both interfaces to activate, and I'm going to deactivate. I have to bring it over here, the rigid link set, since the interfaces are now in place. So you'll notice that I don't have to reactivate other sets. They stay activated. Only when I drag something out to be deactivated will that come off, to say that. And I can only deactivate things that were previously activated, which would make sense. And then the last stage will just be the load, 30 degrees. So in this case, I'm going to drag and drop the static load. Other things that I need to do in this stage is actually go here to control analysis. I'm going to tell the program that I want it to consider the undrained behavior of the clay. And I'm also going to tell the program that I want the load to be applied over 10 steps, and that I want a result for every step. So this will make it nice in terms of graphing. When I'm maybe extracting results and comparing displacements over the load, I'll actually be able to get a nice graph of this increment over, in this case, 10 steps. And that's it. Let's just call this degrees. So now I have my first stage created, construction stage, and rather than go back and do the same thing over and over and over 4 times, I can just make copies and just change the name to keep track of everything. Click modify. And then the only thing I have to do is, on the very last stage, just replace the loads. I can then just replace 30 degrees for 40 degrees, since this is a completely different set of analysis, and I will do the same for the others. But you see how all the other stages where everything was copied. So stage 1 is the same, stage 2 is the same. The only thing is now, again, I'm replacing the loads and just updating the name just for namesake. And lastly will be the 60 degrees. So we've now created all of our stages, and we're ready to then just define the analysis cases. So we've created stage sets, but we need to tell the program that we want to run a construction stage analysis. So we'll go to analysis case general. We see here from the list we have many options of the types of analysis you can run. So we're just going to select construction stage, but you can see we have time history, we have seepage analysis, we have slope stability, all kinds. So we'll just, again, keep matching names, 30 degrees. Here's where we have our 4 sets that we created. And the only thing here is just activate these 2 conditions, these 3 options. Automatic pore pressure consideration, so we can see these forces reflected on the walls of the pile, and to initialize stress and the K0. So we just keep repeating this for the other sets. And now we have all 4 of our cases. So we're finally ready. We just save it and run. And just click OK. Now I'm going to leave this for a second just to show you what the output window looks like once you start running analysis. You'll also get this box. And so what you'll see is, you'll see a progression. We see here we've entered the 30 degrees case initial stage, and you'll get information about if there's any warnings, if there's any issues. You get information about how much time it's taking, stuff like that. So we see here we passed the first stage and we're now on to pile, and it took about 18 seconds. And so this would be happening for every stage, every analysis case. And in the end, we will have a long list of grouped results for each. Which would look something like this. I'm just going to open a model that's already finished. So what we'll see then is we have all of our analysis sets in order, and each set has its own 3 stages. So let's look at the results for the displacement at the 30-degree load. And then what I actually want to focus is looking at the results. I'll come back to the model just to show you, sorry, just to show you specifically the Plaxis tutorial. The only result they show is the displacement for the 30-degree load, which is what we're looking at, what we were looking at in the program, but we're looking here at a screenshot. So we're looking at a maximum of 24 millimeters displacement, and this is the distribution, a max at the point, of course, of load. Plaxis is showing between 24 to 26 millimeters. 26 is their upper bound, but they don't have a specific, I think they just have ranges. So we see that we match pretty well for the tutorial's sake in this case. But from then on out, because they use the rigid object, they actually don't have what would be other kind of results that we're going to be looking at. So from here on out, I'll just be looking at different ways that we can see results that make it very handy for an engineer. One of them being using this isosurface function. So we see here we're looking at the side view. We can activate the max results as we saw in the diagram. So different things we can do is use this thing called isosurface, where you can limit the range of results that are shown by cap. So here I'm telling it not to show me anything below displacements of 2 millimeters. So it makes this a little easier, a little more clear on maybe focusing on what's happening. Maybe in other results, it would be more interesting keeping the range maybe at 4 millimeters, something like that. Other things you can do with the program is you can create multi-step animations. So this was a construction process with 10 load steps. So I can actually tell the program to show me a video of this increment. So once I go here to play, we see the program showing me, in this case it's shifting the maximum displacement around to, automatically, but we have a better understanding. We kept the limit at 4 millimeter cutoff. So you see how even the isosurface itself reaccommodates for what's happening around the model. So that's something you can actually save and include in a presentation like the one that I have in my PPT. So that's isosurface. Something else that might be of interest. So up to this point, we modeled this in a specific way where it's easy to just deactivate sets and show, half of the results, which is again kind of what Plaxis is doing, but we have way more control of that. We have this other command called clipping plane. So I don't have to necessarily be constrained by the geometry in which I initially meshed. I can actually just tell it to clip a plane at any point or in any direction, and then create combinations of results that I want to see. So this, for instance, might make it even more clear of what's happening in this 3D space, since it's clearly based on the lateral, not a symmetric result. So this makes it, a handy feature that you can then easily just go to something like what we have as a 3D to 2D wizard. So this allows us to select points of interest, nodes of interest, in this plane that we've cut. We see here that if we rotate the model, those red dots represent the location of the nodes, and you can actually just select individual points of interest and create a table out of that. So it's very easy to work in a 3D environment and get hard to get results. So that's our clipping plane function. Other thing that you would definitely be interested in, would be something like graphing results. So the program has this command called extract, and we can select any kind of result we want. In this case, let's say total displacements, and you see here you select the set. We're sticking with the 30 degrees, and especially for construction stage analysis, this is very handy since you can see the progress through the process. And so here I can select the node or nodes of interest to graph, or I can actually just directly tell it, just give me a table, do the maximums, the maximum displacements through this whole process, just table that out. And so we see here, this is why it's also nice that we did the 10 increments for the load, because now we can graph this quite nicely. So I'm here in millimeters. I can actually first tell it that I want to just make it a little cleaner how you're displaying it, just show general. I don't like how it looks in scientific for both. So we see now it's much more easier to see what's happening in each stage, and we can directly just select these two columns and either export them to Excel or just graph them in the program. And we can get this nice graph of the displacements throughout the process, in this case the load increment. And then lastly, I guess what we would be interested in looking at would be the results on the pile itself. So in this case, it's the shell element. I'm going to change my units back to meters, since now we're looking at results like moments. Well, forces, actual forces won't matter, but for moments. So here we see our actual forces on the pile itself. This concentration. In some cases you might want to see that a little more clearly if you have structural elements. So you can add this cut-in diagram. Actually, I didn't want to select that. Let's select it again. So starting point there, I'm just going to draw it basically along the face of this and tell it to extrude it in this direction. And we're going to get a line diagram reflecting the results. So we see there, it's a little more clear now where this is happening. It shows the max and the mins. So there's all these different ways to see the results in the program. In this case, we can also look at the bending moments generated by this force on the side of the pile. Which we can see there clearly. And one last thing is you can actually right-click the legend and go to auto range, and it'll maximize the colors a little more. So that's basically the conclusion. At this point, we looked at different ways to extract results, create these animations. In this case, I didn't use the isosurface. I just did it regularly, but this is the kind of video you can insert. And then we looked at the results, the moments, the actual forces, and if you want to see the friction generated between the pile and the soil, you can look at results for the interface. So then the last thing this PDF covers is the other results. So we see that for the 40 degrees, we have a smaller displacement. It's not 24, it's actually closer to 22. Smaller actual force, smaller moment. For the 50 degrees, even smaller. And then lastly, for the 60 degrees, it's the smallest, which makes sense. You're pulling, different angles. It's gonna, I think, create a larger displacement sideways. But that's the part of the test of this analysis. So in conclusion, I just want to point out again, this is based or this was used as a way to compare, to validate, results between the two programs. But the main differences being that in this Plaxis tutorial called 3D loading of suction pile, they only model half the shape. We modeled the full, and this is actually a very simple geometry that we were, generating. This is something common for models in Plaxis. They have very simplistic options for the shapes they can do, whereas we can do any kind of complex geometry, especially with our CAD compatibility. It's very handy for companies to just do their full geometry model in AutoCAD and just import it directly to GTS and just start meshing. And the other differences that I mentioned was that they don't use any structural elements, they just use a rigid body. So the only results they can get are displacements and maybe friction in the interfaces, but nothing like we did for the shell element pile. And they also needed help just to connect the meshes with their helper object, whereas we don't have that difficulty. And lastly, we saw how great GTS-NX is for its post-processor, how we can extract or visualize results, graph results itself, animations, videos, and all that. So that's the conclusion of this training. Thank you very much. I hope you're here for the next one.